Good morning, everyone. This is a short little video to go over the types of formulas and diagrams we use to represent organic compounds. So you'll notice that when we're talking about organic chemistry, we're mainly working with carbon as the backbone of a molecule. So you'll see that pretty often, and it's important to remember these couple of terms up here. Okay, carbon will always form 4 bonds because of its Lewis diagram. Hydrogen will want 1, and oxygen 2. So we should be pretty familiar with those at this point. Whenever we build chains of hydrocarbons, it's with the carbons attached to each other. So we'll go through a couple of examples with this sheet here, and hopefully that helps to clear up the relationship between different types of diagrams. There are 3 types that we use depending on the information that we want to get across. So the first one is just the molecular formula. This tells us how many atoms of each are in a molecule. So if we look at the first example, ethane has a molecular formula of C2H6. So all of these formulas are based on the number of carbon and the type of bonds that they have. So because it's a hydrocarbon, we're telling us that. We know that 2 carbons have to be bonded together. So in this case, they'll look like this. And then the hydrogens fill in the rest of the bonds of the carbons. So each carbon should have 4 total bonds, and the hydrogens will fill in these spaces to satisfy the octet. So we're not looking at exceptions to the octet here. We're purely focusing on carbon and hydrogen. So that's a molecular formula expanded out. A structural formula is what I just drew on the page. So that shows all of the atoms with their bonds. And again, this is for ethane. Each carbon is shown with its symbol and then bonded to a hydrogen. So in this case, you can see all of the individual bonds and all of the atoms that are in the molecule. A third version is the condensed structural diagram. So this just shows us only the carbons and what are bonded to them. So in the case of ethane again, because there are 2 carbons there, we show carbon 1 and carbon 2 with a dash in between them. Now everything to the right of the carbon is what is bonded to it. So in this case, carbon 1 is bonded to carbon 2 as a chain because it's a hydrocarbon. And carbon 1 has 3 hydrogens on it. And so does carbon 2 in this case. So if there was an oxygen, for example, in carbon 2, it would have that to the right of it. So that's called a condensed structural formula. When we have long chains of hydrocarbon, they're a bit easier to draw than the entire structural formula. An example of this now, if we look at this example, ethanoic acid. So we've got 2 carbons again, right? If we were to expand that out, and the dash shows that the carbons are connected. To the right of the first carbon is 3 hydrogens. So we'll expand those here. And then to the right of the next carbon are 2 oxygens and a hydrogen. Now, we'll learn this more in detail as we go, but whenever we see an O and an H beside each other, that's a hydroxide group, which means that the other oxygen has to be double bonding to the carbon. Okay, so we get a structure like that, and we'll get more familiar with it with more examples. To follow that up, you can see octane here. Because octane has 8 carbons, if we were to draw a structural diagram for this, there'd be a lot of different lines. So for something like this, it's easier to show the condensed structural formula. So the first carbon has 3 hydrogens on it. Each middle carbon has 2 hydrogens, and then the last one has 3 as well. We can also condense this even further because we see this unit repeating itself here. I could rewrite this like this. In square brackets, I see 1, 2, 3, 4, 5, 6 repeating units. And I can condense that further. So all of these are acceptable ways to represent a molecule. It just depends on how many variations of it there are and how many carbons we're trying to show. Lastly, and this is the most common one for organic chemistry, is the line diagram. Here we only show the carbon atoms. So we're not going to see the hydrogens, but we know that they're there. And if there's anything other than hydrogen, it will be shown. So let's look at ethane again. Okay. To draw a line diagram, we draw each carbon as a point and then connect them with a line. So in this case for ethane with 2 carbons, it's just a straight line across. Each end represents a carbon group with the maximum hydrogens on it. For something like octane, because there are 8 carbons, we can number these here. 1, 2, 3, 4, 5, 6, 7, 8. What we're going to do is zigzag, and we zigzag this because of the tetrahedral pattern. Each carbon is actually AX4 in this molecule, so the zigzag represents its true bonding pattern. And the hydrogens are just, instead of drawing them like this, you can picture that they're there, but the point of the line diagram is not to show the hydrogens, so that we can simplify the structure and just focus on the carbon atoms instead. So it'll always be a zigzag. You can see here, 1, 2, 3, 4, 5, 6, 7, 8. Right? Each point on the zigzag pattern, or each bend of the line, represents a carbon atom. So now if we go to ethanoic acid, where there's more than just carbon and hydrogen, we can see that there's oxygen. So on the left here, you can see the structural diagram, and on the right, you can see the line diagram. So the carbons have been replaced with points or bends in the line, and then the other atoms have been shown. So that's a property of the line diagram, where we just ignore hydrogens that are bound to carbon. You can see that the hydrogen on the oxygen is still there, and we replace the carbons with dots and bended lines to simplify the structure. Okay. If a molecule has a double bond between carbon atoms, we just represent that with 2 lines on the line diagram as shown. So for propane here, you can see that there are 1, 2, 3 carbons. So I want to zigzag them. I'll draw 1, 2, 3 in a triangle pattern, connect them all with a line, and then a second line between the first and second carbon to represent the double bond. If it was a triple bond, I would just add a third line in like that. So in this case, we can't do that without straightening out the shape, and we'll see that later when we study these type of molecules. Okay, so each of those structures there has 3 carbons. So to summarize this, a great example and a great activity is to go through each of the basic hydrocarbons. So the prefixes tell us how many carbons are in the chain. So for methane, we'll go through, we'll call that CH4, C2H6, and you'll notice a pattern. For anything that ends in ANE, the general formula is CnH2n plus 2. So there's 2 times plus 2 the number of carbons for hydrogens. So if propane is C3, 2 times 3 plus 2 will be 8. That tells us how many hydrogen there are in that case. So for the structural diagram, methane we've seen many times over the years. Okay. Condensed structural diagram, I just draw the carbon and I list out whatever's bonded to it on the right. And then I can't draw a line diagram for methane because a line requires 2 points, and that would suggest 2 carbons. So for methane, there is no option. And even the X is a type of line diagram, so we're going to put here not applicable. Okay, one more example for this. I'll do propane here. Structural diagram, we tend to just draw the carbons in a straight line from each other. Okay, you could also show the zigzag pattern if you'd like. Condensed structural diagram, we do carbon 1. Okay, carbon 1 has 3 hydrogens, so I'll write CH3, CH2 because the second one has 2 hydrogens on it, and then the last one has 3 as well. And for the line diagram, I want a zigzag here, so I'll go 1, 2, 3, and then I'll just connect my points. Eventually, you won't need to draw the points, you'll just know how to draw the zigzag. So for some more practice, consider filling in the rest of this chart, and you'll be able to see the first 10 basic hydrocarbons, and hopefully that helps clear up the different type of diagrams that we use.